Is it? Oh, okay, it's on. So, ooh, wow. So this is the work that Ken and I have been doing. So Ken, in the middle of presentation, if you want to jump in, you're welcome to do that. So I go through the same questions that Norm showed. The first question was that what are the bases of changes that we had since 2008? Obviously, we have much more data, so basically whatever we did mostly is based on the new data and analysis of the data. We took advantage of simulation for hanging wall, but we adopted with the empirical data also. We also changed the range of applicability of the model. For example, we added anelastic attenuation that we didn't have it in 2008. That's why in the figures that Nick showed, 2008, we over-predicted large distances. Now we are doing a much better job. Specific things that we changed, obviously we added thousands of small magnitude data in the database because we over-predicted small magnitude prediction in 2008. Now we are doing a much better job. We adopted the hanging wall model of Jennifer, which is based on simulation, but we put it in the larger model and we regressed, so we adjusted accordingly. We also modified the distance taper in the hanging wall model. We added, as I mentioned, anelastic attenuation, so now we go to 300 kilometers. We added the data up to 500 kilometers, but based on the analysis of the residuals, we are comfortable to say 300 kilometers. And also because now we have lots of data from different parts of the world, we could regionalize Japan and Italy in one package and China in a separate package related to anelastic attenuation. In 2008, we had the depth to top of rupture. During the model development, we found out that if we use depth to hypocentral point, hypocentral depth, the residuals look better, both for various z-tar as well as hypocentral, so we adopted that. Dip angle for a small magnitude is strong. We included in the GMPE. Then after analysis of the residuals, similar to what Norm showed, we eventually settled there is not much difference between strike slip and reverse faulting in terms of prediction. That's where coefficient where reverse faulting is basically 0. Then we have now magnitude dependent standard deviation 4.5 and 5.5 larger in between linear taper, and for a smaller than 4.5 the standard deviations are larger. So these are the key changes since 2008. There are minor changes here and there also if you want. Question 2 and 3 were the estimate of the uncertainty normal and hanging wall factor. So this is our coefficient for normal fault, C9. These are the numbers, periods, PGA, it goes all the way to 10 seconds, then PGV, and these are the values, and these are the basically the error of the coefficient. And this is the same thing, C10 is our hanging wall factor, so this coefficient goes in front of hanging wall model coming from Jennifer with some modification on the distance versus period and the estimate of the error. So for normal fault, relatively coefficients are strong compared, but once you get to say a period of 1 second and longer, so these numbers are not strongly constrained. For normal fault, period of 1 second and longer. Shorter than that is strong. Hanging wall factor is almost everywhere is strong all the way to longer period. The way that it works is that the hanging wall model is good up to 1 second. So we continued using that model of 1 second and computed the coefficient, and it goes beyond that, obviously reduces gradually, and then in the last few numbers it really becomes unstable and we assign 0. So that was question 2 and question 3. Then, since Norm asked yesterday what's going on with 5.5 and less, last night I just extracted this thing from the residual. This is period of 0.2 seconds for reverse faulting, magnitude 5.5 versus Rx. This is for Rx positive, up to 40 kilometers. And then the next one is Rx negative. Oops. Rx negative to 40 kilometers. So not too bad. Let me go back one more thing. So 5.5 and low, even the Agnew-Wall model really is not applicable for that small magnitude, but the overall behavior is not that bad. Question 4, estimate of uncertainty for magnitude 8.5 and 300 kilometers. Obviously, these are aleatory, and then also, as Norm said it, we are relying on the study that Linda and Bob Youngs did it, and this is the figure that from their paper. This is for PGA, strike slip, magnitude 7.5, and versus RX, and this is us. So I don't know if Linda or someone else is going to give a presentation on these things later. Okay, so they're going to elaborate on that. Then sigma of sigma, we haven't done anything and specific on that issue, but we don't have any comment on that. I was hoping that maybe Linda and Bob is going to take care of that. Then big question is that if you remember, Nick showed that our prediction at high frequency, say 10 hertz and a little bit higher, we are higher than the other NGFS2 GNPEs. They ask if you provide reason. Obviously, is comparing one model against other models, so it's both sides. We are trying to explain what's going on. In terms of residuals, this is versus magnitude at 10 hertz. It looks good, so we don't see any major issue in the magnitude scaling at that high frequency 10 hertz. And I examined also 0.05 seconds and others and longer and shorter. Then in terms of distance is also 10 hertz. This goes to 80 kilometers. Again, nothing strange we see. So we are just examining just to make sure that if something went wrong or not. We dig it considerably and we didn't see anything wrong. And then between magnitude 6, by the way, that's everything. And this is between magnitude 6 to 7, 10 hertz, again versus distance. Again, we didn't see anything strange. The other thing, comparing our model versus the other model, as I mentioned, we use depth to hypocentral distance. And I think Nick universally used, or in many cases, used hypocentral depth of 8 kilometers. And for many cases, at least for this project, I think he used ZTAR either 0 or very small. So that can be a little bit source of the difference between our model and the other models. Because if you plug in 8 kilometers, which is obviously a little bit more than 7 kilometer threshold, we get an increase in our model. So that can be one source of the difference between ours and others at high frequency. The other thing that we have not done was we didn't mix anything related to anelastic attenuation and short distance. So short distance is, I mean, up to 80 kilometers is up to 80 kilometers. Then we go to 300 kilometers. So they are basically not much messing up of the near source effect. The other thing is modeling, magnitude scaling. The data is coming from Nick. I just replotted the 5 NGA models versus magnitude, 30 kilometers RJB, strike slip, 760 meters per second. So this is us, basically, and we break it at 6.5. By the way, previously, 2008, we had a break at 5.5 now, because we have lots of data, small magnitude, we have a break at 4.5. So we have 4.5, 5.5, 6.5. So we are high. So we think that this is really modeling issue. If you break it at 6.75 or a little bit less or a little bit higher. So that's the range. In fact, if you look at next plots, this is the range that we are a little bit higher than the others. So in summary, this is a combination of various things, complicated issues and modeling and so on. We believe that in summary, the reason that we get different at high frequency, first of all, is this hinge that we have at 5.5, 6.5. We could do it a little bit differently. The other thing is that is apple and orange comparison. It's not apple and orange, but it's a little bit sensitive. If you assign z tar 0 and z high a little bit less, a little bit higher, we get a little bit higher ground motion, especially high frequency. Then also, as I mentioned, the attenuation, we are not messing with the near source attenuation. Yes?
So this is Ken Campbell now speaking as a proponent. I looked at something else this morning that kind of relates to this high frequency increase in ours. And it turns out if you look at our spectrum as a function of VS30, that we have a very strong shift in the peak in the high frequency content as you go to higher VS30. So if you look at 760, for example, where on the spectrum, our spectrum peaks at around 10 hertz, where the others peak at around 5 hertz. But if we go to soft rock, right. So if we go to like the 550 or so, that shifts to 5 hertz, and then it even shifts further. So we have, this is different from our previous model where we were not getting big shifts in the peak of the frequency, which I think we didn't understand why we weren't getting that shift. We expected to get it. We are now getting it now, and I think this is another contribution. Sorry, Yousef, I didn't have a chance to mention that too.
Good point, yeah, and it's correct. In fact, the shift, we see it, and in fact, we are happy to see that. Then question 7. We have a bump or hump so this is 4.5. This is magnitude less than 4.5, larger than 5.5. As I mentioned, our standard deviation aleatory is a function of magnitude. This is tau, this is phi, and this is total. So there are 2 curves here for each one. So let me go to the next one that we can focus for larger magnitude, then we see it. Okay, it's the same thing, magnitude 5.5 and above. So there is a bump here at the CB13 NGFS2 model around 10 hertz. Then that it translates a little bit bump, obviously is much milder in the total standard deviation. Phi is fine. So the question was that, is it due to the Japanese data that we added and so on? We believe it's not due to Japanese data. And the one reason is that we had almost the same bump. Obviously, everything was lower, standard deviation was lower for CB08. And CB08, we really had only one major Japanese earthquake in our selected database. But it's NGFS2, we have 5 major well-recorded Japanese. So we conclude that since we had it in 08 and we have it in NGFS2, most likely it's not due to the Japanese data. And also it's very important, we didn't do any smoothing of the standard deviation. We did some smoothing of the coefficients and other things and so on, but we didn't do any smoothing. So this is really what's coming out of the data. So that was another question. And that's it. References? No? Questions, clarifications? Yes, Julia.
Do you guys have any questions?
Oh.
I'll start with one. I just want to be sure that from what Ken just added, the shift in the frequency content is related to your VS30 scaling.
I think that's one factor. The shift, yeah, the moving.
Because by the time you're at, you
High
said
fre- high-
400 or 500 meters per second,
Then
then
we
you're
get-
back.
yeah.
So you have a bigger shift.
shift than 2008. And in fact, that's correct. We discussed it 2008 and so on. So how come we didn't
So
see
the
it?
question is, why do the rest of us not see that shift? Right, because we're doing something.
I think you guys have to explain. No, the thing is that definitely, as I mentioned, it's two-way. We see it, you don't see it, so there are various factors, you know. But
And second question, why didn't you smooth your standard deviation?
we discussed it. I think if it's real, we didn't want to mess it. This part, I cannot be discussed internally. I really think something is in the data. What is the reason? I don't know. We discussed it internally. There are some hypothetical and hypotheses and theories and so on that we have to elaborate. This, I think, is real.
But if you smooth coefficients,
Not
shouldn't-
drastically.
Shouldn't you smooth the standard deviation too?
That's a good point that I should mention also. The coefficients also, we did very limited smoothing. Really when, for example, it was something that didn't make sense physically and so on, we didn't do, so if you look at, I don't have it here, response spectra is a little bit not smooth. So we did very minimal smoothing on coefficients just to avoid something that's not physical. And these things we didn't do anything. And especially this 10 hertz, again, we discussed it internally a lot. This 10 hertz, someone has to dig into this. I think there is something into it. Why? We are thinking about a couple of ideas, but it has to be something. If it's in the data, we didn't want really to mess it.
One question for us to think about is, should we be shifting to a lower velocity to use as our reference rock instead of 760, use 500?
You mean for this project?
Mm-hmm.
I don't know.
Or looking at, probably we need to look at the VS30 scaling then of all of these models and the data that they were derived.
And more data you have.
Because that shift is an important one to understand.
That's a good point. Also, obviously, as you know, we have huge amount of data at the lower VS30.
Okay, thanks.
Julian has a question, and Tom hit.
Julian Lozos from Peer. Just a question. You have the depth dependence, or you have a hypercentral depth term. So does then in that case does the burial depth also have an effect here? Because I'm just imagining.
You mean Z-tar to top of rupture? You mean?
Yeah.
We don't have it explicitly for these things unless in other parts of this thing. In 2008, we had it explicitly Z-tar, and we dropped it, and now we have hypocentral depth. Then, I don't have it here, but I have it on my computer. Then we examine the residual versus Z-tar, and it looks fine. But if we do it with Z-tar only, the residual versus Z-hype was not as good. So in other words, when we take care of hypocentral depth, we take care of, obviously, hypocentral depth and Z-tar. The reverse is not true.
Thank you.
Tom?
So we use ground motion prediction equations in early warning, and they have to work over an extremely large range of magnitudes seamlessly. And we did a study years ago, Georgia Koo and I did, going from magnitude 2 all the way up through all the NGA data. And when we did it, we separated the soil and the rock sites explicitly in the regression. So we did different regressions for soil and rock. And they both saturate with magnitude, but they saturate differently for acceleration. It's not true for velocity and displacement. but at acceleration in the soil sites saturate to the same as the rock sites in close, but at all other, well, at intermediate distances, the soil sites are bigger. And if you get out to really large distances, basically you're looking at such low frequencies that the soil doesn't make so much difference anymore. So once you do the regression in terms of separating the whole thing between soil and rock, I think it gives you more flexibility than trying to build all that physics into a site correction.
Well, we used to do it in 2 generations before. It was like what you just said, soil, rock, and then we combined it in one factor, S1 and 0 for soil and rock, and now we are advancing to that. So
the point is they saturate in different ways.
You mean
at different
magnitude versus
distances.
magnitude.
Versus magnitude. So when you get in close, you see nonlinear attenuation. It limits the peak acceleration in the soils. When you get out far, you're mainly looking at very long periods, and at very long periods, it doesn't really care whether it's a soil or a rock. It's too long a period to care. And so the physics that goes on here can be pretty complicated, and try and put all of that stuff into site correction can be pretty complicated too.
Yeah.
Yeah, this is Ken Campbell again, speaking as a proponent. So Tom, yeah, we have a VS30 scaling model, and what we found was, we looked at it very carefully. What we found was that it's very robust, and it's really not correlated with any other parameters. So basically, we could put it in and fit it with the rest of the parameters, and it didn't really matter. I mean, whether we put in other parameters, took them out, and that sort of thing, the VS scaling was very, very robust and didn't change much. So we don't feel there's an issue with just having our VS30 scaling model as part of the overall model when we fit it. Now, remember, we're using random effects, so in fact, we are sort of separating the within and between earthquake factors when we do this, but that's another issue. The other thing is that there is we do have a nonlinear soil model which predicts the behavior that you're exactly discussing, so that the rock motions do tend to saturate, but at higher levels than the soil because of the nonlinear behavior. And then lastly, you're talking about long periods. Basically, we have a depth Z2.5, a depth to the 2.5 kilometer velocity horizon, which is a very strong effect for the long period. So it turns out sediment depth is important at long periods, but VS30 scaling is important at short periods.
Is this on? Add to that, Tom, your comment that it gets very complicated, and our models are really complicated, and that's part of the reason why when you try to parameterize all of this stuff into coefficients, you get pages long of equations, right? And that's the penalty for that part of it. Yeah, 3 pages or something. So the site response part is complicated, but by using the data together, we're able to sort of help constrain parts of the magnitude scaling that may not be as well constrained by rock, because we have a lot more soil sites. We're kind of trying to borrow strength from where you've got it to help you apply the model into the other parts. But that complication is what people complain about, but it's required if you're going to try to capture all of these effects.
Sina?
Hi, this is again Sinan from METU. About this period shift, the peak in the short period. I mean, do you observe it, Ken? Because you just addressed it. Do you observe it in short short distances, at short distances and high magnitudes, or because I mean that kind of effect can be related to nonlinear side effects, as you we are discussing. And it could be not the shift in the period, but it could be sort of broadening of the peak.
Yeah, so we produced a series of plots. In fact, in our peer report, we have a series of plots where we plotted the spectra for the 4 NEHRP site categories, B, C, D, and E. And we plotted it for different levels of PGA rock motion, right? Because that's the parameter that controls the nonlinear behavior. So if you set that PGA value low, you're looking at linear behavior, you're still getting the shift in that peak. It does look a little more like broadening as opposed to a very strong shift in the peak, but the broadening is bringing the peak, is shifting the peak. It broadens and shifts. As you go to high ground motions, then you're getting a very strong shift in the peak, obviously, because of the nonlinear behavior. It's still there, though, in what we would consider at 0.1 G, for example, nearly linear behavior.
Yes, Gabe.
Just one thought, perhaps heretical. Could those two issues be related? The shift in the peak, or the high peak at high frequencies, and the high sigma around 10 hertz? There's simply lack of fit?
I don't think so, because I mentioned that in 2008 we didn't have that shift, but it's still there.
Yeah. But they're happening at the same in the same place.
Yes. So I hope Tom Hanks is here. Someone has to dig into that. I think this is real. Should be a reason for that.
Yeah, Ken Campbell again, speaking as a proponent. Something very intriguing, and it's just an observation, but I'll throw this out there just since it's coming up as an issue. But if you notice, the peak at 10 hertz is roughly around the peak in the vertical spectrum. The dip at around, whatever that is, yeah, that dip right there is about the peak in the horizontal spectrum. So, you know, I just throw this out as something that is totally unexplainable, but could have some seismological basis to it. I don't know, but it's just an observation. I brought it up to Yousef.
And also it's in tau only.
Yeah, he chose not to present that because it's very speculative, but you know, since it is a discussion topic at this point.
And also, I believe we saw in the earlier version of Brian's standard deviation before smoothing that also they had it about 10 hertz. So if I want to guess, there's something in the data, but I don't know the physics, what's going on. Any other questions? All right, thank you very much.